Guys, welcome back. It seems like just seconds ago we were talking to the grade 11s. Grade 12s, welcome. Grade 11s, welcome too. But grade 12s, I hope you hanging on to those couches and you're ready to do some amazing work, learn more and learn extra. Don't forget, I know I keep telling you, you're probably sick of hearing me, but I want to chat to you on Facebook. It's facebook.com/learn extra, and that's with an XTRA. Also on Twitter, @LearnExtra, XTRA. Today we are chatting about motion and its physical science, grade 12, and we have a fantastic teacher named Tracy. She's got a fabulous laugh and she's going to take us through today's show, and it's going to go like this. So stay tuned. And Tracy, hi.
Hi, Indian.
How are you today?
Good, and you?
Okay, good. Tell us what you're going to take us through today.
Well, today what we're going to look at is we're going to look at vertical projectile motion. For a lot of the grade 12s, it should be revision from grade 10 with a little bit of extra maybe. Graphs were probably forgotten because it's been a while.
No, but it's
but
good.
We're going to look at vertical projectile motion, equations of motion.
So if anyone has questions, they can send it through to us. We'll be here to answer questions. And Tracy, let's get down to vertical projectile motion.
Great, thank you very much.
Okay.
Well, guys, we're going to look, like I said earlier, we're going to look at vertical projectile motion. And what we need to remember, and I've sort of drawn a picture, it's just an indication, is projectile motion has three ways that we can show it. And essentially, what we're looking at is motion that's going up and down. All right, we're forgetting about horizontal now. We don't worry about that. We're looking at objects that are either going to be dropped, so we just drop them, or throw them straight down, or an object that gets thrown up, straight up and caught, okay? Or we're going to consider objects that can be thrown at an angle, okay? Now, we're not concerned with what happens in the horizontal motion because that's irrelevant at this point. We're only looking at one dimension. What we need to remember, and I think this is the thing we forget, is the fact that gravity, and we remember this from grade 10, gravity is 9.8 meters per second squared. Please remember, because this is what fascinates us, is the fact that gravity always acts down. And the best way to remember that is you go, well, if you jump up, which way do you go? You end up down, okay? And if any of you don't, then I want to come live on your planet, okay? Because we know that gravity always acts down. We know that it's 9.8. Please be careful, especially if you're using old textbooks. A lot of this is the same from the old curriculum. If you're using them, they'll give you gravity as 10. We don't use it as 10 anymore, okay? It's got to be 9.8. It messes up the calculations, but it's okay. It's more accurate. Remember, when we look at our motion, the velocity up is equal to velocity down. What this means is if I throw an object up and I catch it in exactly the same position, whatever velocity I threw it up with is the velocity I need to catch it with. Okay, it can't change. The only reason why this works is because we're ignoring friction. We're ignoring air resistance. We know that's an issue, and we also know that in reality the shape of the object, if it's a ball or a piece of paper or a feather, does play a role, but we're ignoring all of that. Otherwise, the maths just gets complicated, and we don't want to do that. We're trying to get the principles in. Also, when an object gets thrown up and down, the time it takes to go up is equal to the time it takes to come back down to the ground, or wherever its starting position is. That's very important because what happens, maybe I should draw, what happens here is they'll often tell you, and we're going to look at a problem where an object gets thrown up in the air and returns to the person's hand in 2 seconds or 10 seconds or whatever the case may be, and then you go, I don't know what time it is. We do. We've just got to turn it up. We've just got to halve it for going up and for coming down. This is the big, big, big thing for us, is direction. If you're using, and it's your choice, there's no set standard to this. There's nothing that says, well, down has to be positive or up has to be positive. That really is your choice. But if you choose the upward direction as positive, in other words, I throw an object up and I go, anything that goes up is positive. Acceleration is negative. This is where you're going to make the biggest mistake. Acceleration must be negative then. If I choose down as positive, then my acceleration is positive. and you can't change that. This is just another, it's part of an exam tip. Some of you might have done this at other times, but what you need to remember is you choose the sign convention. So when you're answering the question, you're the one who decides it's got to be, I'm going to choose up as positive, down, whatever, okay? And you've got to stick to it. You're not allowed to change that halfway through your question, because then you've actually started a new set of motion, and that can't happen, okay? Now, what does that mean for us? Well, in terms of calculations, your equations of motion still stand, and I'm hoping you recognize these, okay? So we know that final velocity, Vf, is equal to Vi plus A delta t. All four of these will be given on your information sheets in your exam, which is great. I just want to highlight one thing for you, because this becomes a problem. I have delta y there, and there, and there. On your information sheet, they're going to give you two sets of equations. They're going to give you Vf squared equals Vi squared plus 2A delta y, and they're going to give you one that says Vf squared plus Vi squared equals Vi squared plus 2A delta x. That delta y is important. It is displacement in the vertical direction. Okay, so be careful. In grade 10, you would have used delta x for everything. Okay, and you've used delta x last year, you did a little bit of work, you're going to do that again, where you use f delta x, I'm sure you remember that at some stage, and that was generally horizontal motion. But now, because we're looking at vertical, it's like your x and y axis in maths. Your x-axis is horizontal, your y-axis is vertical. So whenever I look at displacement, I have to use delta y, okay? All of these are still valid. But what do we need to remember? Because there's going to be certain bits of information that are just implied in the question. Like, we have an object that drops. Starts from rest, is dropped, takes 10 seconds to hit the ground. And then you go, ooh, okay, I know the initial velocity is 0. I know time, but I'm given nothing else. But you're told what the acceleration is, which is 9.8. So be careful here. They're not going to tell you it accelerates due to gravity. If it's vertical motion, you're going to use 9.8. There shouldn't be any reason why you use something differently, okay? And if it is, they need to give you enough information to do that, okay? Now, that brings us to a fun concept called terminal velocity, okay? Now, when we get terminal velocity, it actually only happens, we can get it in air resistance, sorry, 9.8 is only in a vacuum, okay, or for small objects covering small distances, which is what we sort of do. But think about those people who like to jump out of aeroplanes. Not something I want to do anytime soon.
Oh, no.
No, not at all. It doesn't really, yeah. Anyway, so they jump out of an aeroplane, and before they pull their parachutes, I'm hoping you've all seen this, they fall horizontal, and then if you actually watch them, it actually looks like they slow down. But now I'm telling you that they should be accelerating at 9.8. So what is actually happening here? Well, in the real world, we have air resistance, and air resistance pulls up on them. And what happens is, under normal circumstances, okay, we should have the weight of my person jumping out the aeroplane, or whatever object it is, which is mass times gravity. You remember that from grade 9, I hope. And then the force of the air resistance. So what happens here, and if I can get my little, I should have a mouse here. There we go. Now, what that means is when I look at the resultant force, I'm hoping you remember that, the resultant downward force is bigger than his weight. So he's going to accelerate for a little while. And so what that means is his acceleration is greater than, well, smaller than gravity, but it's still accelerating. But then there comes a time where the two forces are equal. That does happen. And what happens here, there we go. Okay, it's gone away. There we go. Your resultant force is now 0. That means, if you remember from Newton's second law, that your acceleration is 0. Force up equals force down. Very special circumstance, and they will tell you about it. And terminal velocity only happens, there's got to be a certain, you can't get terminal velocity throwing a stone off the 3rd story of your school building, so don't do it. Okay, now, last thing we need to look at, and I'm pretty sure you're all groaning right now because now we need to look at graphs of motion. And we all hate them, I agree, but you are going to get them. Okay, they love graphs of motion, and there's certain things they're going to ask you about this. One, there's going to be interpretation. So they're going to give you a graph and they're going to say, what does it mean, calculate things, draw the graph, that sort of thing. Or they're going to give you a problem and tell you, draw the graph. Either way, okay? Now, in terms of your displacement, I've got a free-falling object, so I'm saying, well, I'm just letting an object drop, okay? When we look at the shape of the graph, now let's consider an object that I'm actually going to throw up and catch. Displacement, I'm hoping you remember, is a vector, which means displacement has direction. Okay, it's very possible for there to be a negative displacement, but if we remember from our graphs, the displacement, when we have uniform acceleration, your displacement, remember, it's getting faster and faster and faster. That means that your object is going, or slower and slower and slower, it depends on direction. Your object's change in distance every second is different. So if I'm throwing an object up and down, what will happen is I get this. These are nice because it actually gives you, it looks like the shape it draws. Okay, it goes up, it comes back down. Displacement is 0 because it ends up in my hand again or wherever I threw it from. Distance is different, but distance can't be a straight line either. Distance is a scalar, doesn't matter about direction, but remember when we go to look at distance, as my stone or whatever it is thrown up, it goes up and it starts to slow down, then it changes direction and it speeds up and it changes the curve. So pretty much it's like taking this graph and taking the second half and putting it on top. Distance, we don't care about direction, okay? Then, what about the velocity time graph? Now, this is where we all get a little shaky because we go, hang on, it's changing direction. Absolutely, there has to be a negative side to this graph without exception, okay? The nice thing is that it's constant acceleration, which means it's going to be a straight line. So depending on the values we have, we would work them out or they'd be given. And I've taken up as my, should we try that again? So that it actually draws a nice line.
Sneaky board.
I love these things.
Hey, they're amazing.
You like erasers.
Hey?
They're brilliant.
Incredible.
It's a good thing. I'm good at this. Yeah. Anyway, so remember, I chose up as my positive direction. So as it's moving up, it gets slower and slower and slower, which is what my graph is showing. It gets to the top of its motion, which is here, changes direction and comes back down, so it's negative now. Can't be positive. But if we consider speed, speed is the same as displacement. It is a vector, scalar, sorry, which means the speed's direction is irrelevant. So we know that when we look at it, my object gets smaller, its speed gets smaller and smaller and smaller, reaches 0, changes direction, and now, and it should be at the same gradient, and it should actually be in line with each other. So let's just try and put them together. Doesn't want to do that. There we go. What should happen, there we go. Ignore all the little dots and stuff on the side. Sorry about that. But at this middle point here, okay, where I'm just going to show you what I mean, this section here, which is now one big red dot, at that point, that's when it reached the top. It stopped, speed cannot have a negative direction at all. That's not so bad. What about the acceleration? We've seen what happens when we get to the top of the motion, and this is the one that gets you guys every single time. We said up is positive, acceleration x, down, which means acceleration is negative. Acceleration is due to gravity, never ever changes. Straight line, ooh, that is a straight line. Negative for the whole time period. It cannot change direction. Okay? That was a very quick overview.
No, it was good. I've got a few questions, so that's
Excellent.
okay.
Brilliant.
Shame. Samuel, don't worry, Samuel. He says, so the graph of displacements never change. And then Lebs has said confused too.
Confused too. Okay.
So maybe they're a bit confused.
No. Okay. So if I'm understanding the question, you're asking me if it's always going to be that nice curve that I showed you here.
I think that's
what they're asking me. Okay.
Yeah.
Not always. And it's Lebs and?
This is Samuel and
Lebsa. And Lebsa, sorry. Samuel and Lebsa. This shape that I drew is for an object where I'm throwing it up and catching it again. Okay, so this one shows it's a nice direction, but let's think, and I'll just quickly do it here. What happens if, for example, it is a graph where I'm telling you I'm dropping a stone, okay? So we're gonna have our axis like we would have normally. Okay, so there's our two axes, and this one is my displacement. So that's terrible.
That's a very thick pen going on there.
It is. Okay, let's just make that y. I'll change that in a second, and that's time. Okay. Now what we said is we've got an object that's doing this, that's falling to the ground. Now as it falls down, it gets further and further apart. Logically, I'm hoping we all realize, well, which way do we want to make positive? Down, because that's the way it went. So we know it's going to, if this is my starting position, okay, that would be like displacement 0 at the top. It's going down and getting further away. So now we've got to think about it and go, okay, as it's coming down, is it speeding up or slowing down? I'm hoping you're screaming at the TV right now, or someone's Facebooking us and saying it's getting faster because it's accelerating, which is exactly what's happening, which means as we start, and then it gets faster and faster and faster, and then it speeds up, okay? So your graph will change shape depending on the circumstances and depending on the information you're given. But what we're looking for is that when it's accelerating, getting faster, your graph gets steeper, and when it's slowing down, your graph the gradient gets less and less and less, okay? So it's difficult when you just got to talk about it. Often if we have values, it makes it a bit easier. Okay, I'm hoping that cleared it up a little bit for them.
I'm sure it did. Okay. Are you ready for another one?
We can do this.
Okay. This is what I love. I love asking the teachers questions. They never know what's coming, and half the time I'm like, I hope this is the right question. So here we go.
Okay, let's go.
Spamandla wants to say, are we tested on projectile motion in 2D?
No, not at all. We're so grateful. Very grateful. It's out. It is going to be in some of your textbooks still, though, because it was in the curriculum for a long time. But it shouldn't be taught. And if you are taught it by your teachers, then I would say be very polite. Don't be rude.
Very nicely. Yeah, never be rude to
teachers. Very nicely ask them to please check with their subject facilitators in their district, so they can get it from the subject facilitators in each district that will then be told. But it's actually been out for... Actually, since the beginning, they put it in, and then we didn't even get asked it in the first exam, so it's gone.
I remember when I was at school, hearing something that was out. It was always very exciting.
Oh yeah, it's lots of fun. It's fun crossing out pages.
It's out.
You can take it out your book.
Yeah. Okay, and then here's another one. Is it true? How true is it that the path taken projectile is called a trajectory path?
Yes. But that's more valid for when we're looking at 2D motion, because that would be when I throw something at an angle. But the trajectories, I'm glad we don't use that word very often, is simply talking about the path it goes. But they won't often talk about that because it does refer to the 2D motion.
Okay, fantastic. Well, what I think we should do, perhaps we should go to a break, and then we'll come back. We've got a few questions on the wall. I'll take Tracy through them. I know Tracy's got a few other tricks up her sleeve, and we can have a little bit of a break. So guys, go get something to drink and be back in literally 2 minutes. See you after the break. Welcome back, guys. We are reaching the middle of our grade 12 physical science lesson. Can you believe it? Tracy's here with us and she's taking us through motion. Rory-san, thanks for so much for giving us your comments. She says, here I am jumping in, Tracy.
It's okay,
once
go
again,
for it.
I like to surprise her.
That's okay.
Yeah. So Rory-san said, so acceleration time graphs and velocity time graphs are similar in shape?
Yes, they're both going to be straight lines, but your acceleration time graph is nice in this section because it's always a horizontal straight line, whereas your velocity time graph will be at a gradient. We'll have a gradient which must always equal 9,8.
Fantastic.
Which makes it
Okay,
easier.
so we're going to carry on the next question, and then after that we've got a fantastic Facebook question from Mbali. And Mbali, if you're watching, Mbali Redebe, you know what the question is. It'll be up after this one. So let's take it away, Tracy. Last 30 minutes.
Excellent. Okay. Well, we're going to talk a little bit more about graphs because we realize that's definitely more the issue than the actual calculation. So what we have here is we have a very simple problem with a nice picture which makes it a bit easier that says consider a ball that falls vertically from rest for 5 seconds. Okay? So they're telling you the ball falls, hits the ground, and then bounces vertically upwards, returning to its original height after 10 seconds. Now this is unusual because we're assuming no air resistance, which is great, but we're also assuming no energy loss. Now you haven't done work energy and power yet, but you will realize when you get there that there's absolutely no way that can happen. I'm sure you remember from momentum last year, we're pretty much saying this is like a collision, okay, and we're not considering energy. Now, what we're going to do with this is we're going to draw the graphs, and that's exactly what a question like this would say to you, is draw the distance graph, the velocity graph, and the acceleration graph, which we're going to do. But we can't draw those without knowing the values. Okay, so it's really important that we get the values in here. And what we're going to do is we're going to take downwards as positive. And what I've done over here, and I make my own learners do this, there are no marks for this, but I do this when I work out a problem, is I make a note for myself as to what the positive direction is. Because we tend to forget. We tend to go, I can't remember, and halfway through it changes. The reason why I've chosen down as positive, and you could have chosen up as positive, is because the easiest way to remember how to choose a direction is to go, well, what's the original direction of motion? And whatever that is, that's your positive direction. It just makes it easier. It gives you, then you don't have to keep remembering, am I using up as positive or down as positive? And sometimes it doesn't go in both directions. So if you always saying to yourselves, well, down's going to be positive, and then they only give you something that's going up, you're making your life difficult because then you've got all these negative values that you don't want to use. So with the information I've got, I need to know, before I can even vaguely think about doing a distance graph, I need to know how far did it fall. Now the nice thing is it falls from rest. Rest means initial velocity is 0. They told you it takes 5 seconds to hit the ground, so I know time. And my equation should be a y there, but that was me, not an x. And I know a, okay? So that means if I look at this and I calculate, we're going to put that over there, we can calculate our values quite easily. I haven't done all the calculations because I'm pretty sure you guys can manage. Remember, and this is a very, very important point, when you substitute in a 0, so we've got 0 times 5, sometimes, especially if you look at some of the older textbooks, because this hasn't actually really changed, is they would just write delta x equals a half AT squared. That used to be accepted, but it's not anymore, because in physical sciences, this 0 has value. It means something to us. It's not just an empty space, okay? So you have to include it, and that's across the board, okay? But just remember, and we all do this when we get all shaky in the exam, 0 times 5 is 0, okay? And then we've calculated and we get 122,5, which means that my object, if I don't kill myself on my mic, has gone down by 122,5, but then it goes, there we go, but then it goes up by 122,5 as well. Okay, so this isn't just for one, this isn't the total displacement, it's just one direction, okay? But we haven't got everything we need yet, because now I've got distance. Okay, let's look at the distance graphs, let's look at those first. So that's where I get these values from. This is a sketch graph, which is what you're going to get asked to do. They're not going to ask you, hopefully, to draw a proper graph in the sense that you've got to do a nice little scale, and because that just takes far too long. But they are going to ask you to draw sketch graphs with relevant information, like I know that it's 122,5 and 245, and the time frames that we were given, okay? Now this is this first graph is distance. So we go, okay, well, what happened to my object? As it comes down, it's a lot like we did the last one, it's coming down and it's getting faster and faster and faster. So if we draw this in, it's coming down and it goes faster. Ooh, that's not going to work. I need to draw a little bit smaller than that. Let's do it in that one rather. It's getting faster and faster and faster. There we go. That's a much better line. Not even sure what I did.
It's a very good line there,
it's much
Tracy.
better actually. You can actually see what it's doing now. Okay, but it's getting faster and faster and faster. It hits the ground and now it's going back up. And we're going, well, acceleration is going to make it slow down. So it's going to go slower and slower and slower, and then it goes there. So it's got that nice little curve. That's because the actual direction is irrelevant. But what about the displacement? Now, all we've done with this question is instead of throwing it up and down, we've bounced it on the floor. So it stopped and started at the same place, which means this point, I'm going to need to stand here, and that point is my beginning and end point. Be careful now with the height, because it only goes to 122,5. So this is a much smaller graph. Okay, be careful here. And there must be this distinction because this has direction. So my displacement, the direction is important. Very, very important. Okay? Hopefully sort of making a little bit more sense for you guys. Now, the next graph is the speed and velocity graphs. Now I've already pre-prepared these and you go, well, I only know one speed. It started from rest, which means I need to work it out. Once again, I'm only taking one direction. So when I do this one, let's just move that over there. We work it out, and this is where working with 9,8 is a real pain because we get 49. Okay, so also this is something you need to take into you need to take this into consideration when you're looking at old textbooks for questions, okay? Is they used to work these out with 10, so sometimes the answers don't work out so nicely anymore. And it's hard to work out questions, so they work out nicely now. All right, so we get 49, which means when it bounces on the floor, it's 49 meters per second. Speed, what does it do? Well, speed, we know it's going to be a straight line. We spoke about that earlier. And it is literally just going to go from here, and it goes up, gets to 49, and then what happens to it? Wow. Me and this board are going to have to make friends. Okay. So ignore that. Okay, you shouldn't have that. I'm so sorry. I don't have one of these in my classroom. Can you tell?
I know. I don't have one of these at home either.
I wouldn't mind one of these at home. Yes, I'm a nerd. I'm a science teacher. Anyway, so speed, not concerned with direction. Velocity we are. Now we've chosen down as positive, which means it starts at the top. At 5 seconds it goes through 0, and then it goes back to 10. So the nice thing is, it's a nice straight line going through the axes. Can you see the shape sort of looks the same? It just doesn't always follow, it just depends on the question. And then, because now in the last example when I showed you, I said 9,8 was negative, but we've chosen down as positive. So that means my acceleration is positive, 9,8. But we needed to have the values, okay? I'm hoping that sort of cleared up some of the problems.
Totally.
Excellent.
Yeah. So
yes.
I think before we get on to Mbali's question, we're going to take a short break, and then we're going to head into our last few minutes of the show.
Sure.
Guys, matrics, if you start early, I promise you're going to fly through those matric exams. Trust me, I know, I was with the matrics last year. If any of you do know matrics that watched last year, ask them, and I'm sure we definitely help them out. Any questions, let us know on the Facebook page, and we'll try and get them through in the last 15 minutes. See you after the break. Hi guys, and welcome back. Hope you're all watching and hope you're loving the show. Tracy, I think we've got a Facebook question.
Yes.
Yes, except I have to, you know what happens? Sometimes there's a few gremlins and you know, they attack the computer. So I wanted to say, guys, I hope you've been tuning in, grade 12s. I hope you're learning lots. Just keep chatting to us throughout the year. We are here and we're available to answer any questions. Tracy, what I think we should do while my computer's having its little freak out,
its moment,
we'll just let it have its moment. I'm sure it'll get over it soon.
Brilliant.
Maybe you can tackle one of your other questions. And
I do actually.
Do you?
Yes, I do. I do have one where I wanted to look at something where we actually do a calculation.
Okay, so Mbali, I'm sorry, we're gonna tackle your question after this.
Yeah, we are gonna get there because his was actually
it was a really good one.
But we don't want to focus the whole lesson on graphs because they are gonna have to do calculations.
Yeah, so let's have a little graph break and.
So what I'm gonna do is I'm going to give you the question. It's not going to come up on the screen, but it's actually quite a simple one. What I'd like to really get into, and it's not for marks, what I'm going to show you to do, but it really is something to help you with the whole concept of, a lot of times you look at a question and you go, I don't even know where to start on how to answer it. So what I teach my kids to do is take highlighters or colored pens or something, or even just underline with your pencil as you're reading the question, and you underline all the important information, and then you put it into a list, okay? So here we have a question where it says you have a ball thrown vertically upwards with an initial velocity of 10 meters per second. So what they're saying to you, now I also like to draw a picture, which my learners at school find quite hysterical because I can't draw to save my life, but we'll just make it a very simple picture. So we have a ball that's thrown up. Okay, now that ball gets thrown up, and what we're going to do is we're going to make this so it's not quite so thick. Okay, it gets thrown up, and what happens is the initial wow, sure, it likes my hand too.
Hard lesson too now. Hey?
I know, and that's the scary part when it comes to me, is 10 meters per second. Okay, now that's the information given. That's actually a ball. Okay, it doesn't look like one, but just. See, I can't even draw circles.
No, the learner's imagination is fantastic.
It's brilliant.
You should have seen John McBride drew a spaceship last year. It was fantastic. It was fantastic. Mm-hmm. Yeah.
Okay, if you were living on John planet. Probably. Yeah. Anyway, so they have said nothing else here. Okay, vertical motion. They have said nothing about the direction you need to choose as positive. And then they ask you in the question, the first thing they ask you is, what is the maximum height? How far does it go? So you go, okay, well, they're asking me for delta y, all right? Choose the direction as positive, and remember I said to you before the break that we're going to choose the original direction as positive, so up is positive, okay? Which means my initial velocity is going to be 10. And now a little piece that I actually didn't spend a lot of time on, which is the velocity when it gets to the top of its motion is 0. So without telling you, it's implied knowledge, they're saying to you that your final velocity going upwards is 0. Implied piece of information, very important. They've also told you that acceleration, now I've chosen up as positive, which means that's 9,8 meters per second squared negative. And what they want is, in this case, they want the delta y to start off with. Now, if we quickly scroll back to our equations, okay, which I gave you earlier, okay, now, how do we choose which equation to use? Because this is actually an important skill. So, we go, okay, let's take my highlighter and decide what I know. I have final velocity, I have initial velocity. Let's get rid of that red because I don't want, red. Let's do that. So that's gone. So I have acceleration. Ooh, we're doing well here. Acceleration. I did one time, so that doesn't help me very much. But if I look at the next equation, I have final velocity, initial velocity, acceleration, and I'm looking for y. Done. You don't have to remember all your equations, and that's the important part here, okay? So we go back, I'm sure I can get it this way. Let's go back to, there we go. So we go back to our question, and now we know that I need to use the equation that says to me that, oh, and it's very thick. Let me see if I can make this. I don't know why it doesn't want to stay like that. Vf squared, okay, equals Vi squared plus 2a delta y, okay? We like this because it's substitution, and remember I said to you as well, do not forget the zero substitutions. So Vf squared is 0, but it's going to be 0 squared. We know Vi is 10 squared, and then we have 2 minus 9, minus 9,8, and I keep running out of space. I write too big. Okay, sorry. It's all about space.
It's all about space.
And that's quite a nice science concept at the same time, so
Okay.
it's okay.
Yeah.
There we go.
Scientists like space.
We do.
Yeah.
I think most of us are from space. We have our equation. Now it's just substitution and changing it up. So 0 squared is 0, so we're not going to worry about it. 10 squared is 100. So, and when I take it over, I'm skipping some of the maths, but I'm hoping you guys are all following me. It becomes minus 100, and we get minus 19,6 times delta y. This is brilliant, because what happens when I take a negative number and divide it by a negative number? I get a positive number, which is exactly what I should get because I chose up as my positive direction, and I'm looking at an object that's moving upwards. So my displacement should be up. I'm going to divide both sides by minus 19,6, okay? And remember, the rule is you take your answer to 2 decimal places, and we get 5,10 meters. That's actually fairly high, and 10 meters per second is 36 kilometers per hour. So this is quite a strong throw. I definitely couldn't throw something that fast. Okay, I'm hoping we all sort of following where I went. The other question they can ask is, how long does it take for the ball to return to his hand? Okay, so now they're saying, how long does it take to go up and come back down? So now they want delta t, and we can do this in one or two ways. The best way is actually to consider the upward motion, and remember that the time it takes to get up is equal to the time it takes to get down. So I've worked this out. That's 5,10, and now we want delta t. Okay, I don't like to use something I've had to work out if I can all help it in a question, because if for some reason this answer is wrong, then my next answer is wrong. Sometimes you have to, you can't get away from it, but this we don't have to. Because of the information we're given, I could actually say, well, we can use the equation, or not that one, let's stand here, Bf equals Vi plus A delta t, and my t's gone for a run. Okay, so that's 0, and that's 10 minus 9,8. Please put it in brackets. This is just a layout thing, because often if you try and substitute this in and you forget the plus side and you don't put this in brackets, the plus and the minus gets a little mixed and you forget what to do with it, and then it just becomes a silly error that you can avoid. We get minus 10 on that side, minus 9,8. We divide both sides, and now we get a horrible number, which is that the time it takes to go up is 1,02 seconds. But that wasn't what I asked you. I said to you, how long does it take to go up and down? So this is very important, because the way we write this is important. You can't just say, therefore, t equals, and you times by 2, because mathematically that makes no sense, and we don't know what you're doing. So what you need to write is, it's almost like, remember word sums from maths, where you had to give your answer as a sentence? It's the same thing. So we're going to say, therefore, my total time is equal to 2 times this 1,02 which then makes it 2,04 seconds. And that's my final answer. Remember, your examiners can't mind read. Okay, we're not bad at mind reading our own kids when we have them in front of us, but we don't see you. So when we're marking, we need to know what you were thinking. So you actually got to spell it out for us, okay, to make it easier for us. I'm really hoping that helped. Do we have any questions, Indiana?
Well, we do. Let's see what we can, tackle.
Yeah.
There's quite a few. Let me have a look here. Shabalala.
Yes.
And you know what? The mindsetters are making fun of me the way I'm saying their names. Rory Sangan and Bali said they like the way I say the name, but I think they're being silly with me. But you know what? Tomorrow I'm going to practice, and then I'm going to be back with those names. Girls, you watch.
I think we need to practice together.
Yeah, I think so. Okay, let's have a look.
Yeah.
Spusiso, she says, why do we ignore air friction? And we've actually got 2 or 3 more questions.
Why we do that?
Yeah.
Because it makes our calculations easier. If we start adding in air resistance, then we're going into Newton's second law, and in reality, it starts becoming a calculus issue. And at school level, what we're trying to do is get the concept that you understand how the motion works, and we reduce it down to basically its base levels. So that's why we ignore it, just to make the maths a lot easier than anything else.
Okay, I see. So hopefully that answers it.
Yeah.
Tato wants to know, he said, so a feather will reach terminal velocity quickly. I think it was with regards to what we were talking about earlier.
Absolutely, because a feather has a very large surface area and it's got a very small mass. So because it fans itself out, it catches the air more quickly. And that's also why when you see a feather, it always looks like it's floating down. In fact, it doesn't accelerate very much at all. It reaches it very quickly,
It reminds me of that joke. How does it go? I don't even know why I'm about to tell a joke on live TV, but anyway.
Okay.
What's bigger, a ton of bricks or a ton of feathers? What's heavier?
Don't you know it's a ton of bricks? What weighs more? I know, I get that all the time. We do the same.
What weighs more mindset? Is a ton of bricks or a ton of feathers? Let us know.
Absolutely. No, we get the same all the time. I know.
Okay.
Absolutely.
Let's have a look. Should we? You know what? Are you ready? Are you ready to tackle Mbali's question?
Let's tackle that one with the bouncing ball.
Yes. Okay.
Okay.
Now, obviously, this always happens to me. As soon as
I find it,
it's gone. Okay. Are you ready?
Yes.
Mbali Radebe, and stop laughing at the way I say your name, Mbali. She wants to know the bouncing ball analogy. Please. She's begging with puppy eyes. And their graphs. So please, can you go over the bouncing ball?
How can we refuse puppy eyes?
No.
Okay.
We can't.
We can't. Bouncing balls are the bane of our existence. I hate it when they give you bouncing ball examples. But what you need to do is you need to be thinking it through in your head. So in your exam, you take a couple of deep breaths and you picture what's happening in your mind. Now, let's consider, because they can do it a whole bunch of ways, but let's consider a ball that's dropped, okay? And what will actually happen is the ball, when it's dropped, so it starts, and its motion is going to do this. It's going to bounce, and then it bounces, and then it bounces, and then it bounces. And what they do with bouncing balls is we realize that in reality, because this is what makes this difficult, is they don't go back to their normal height, okay, their original height. And then they say to you, draw the displacement graph and draw the velocity time graph, and then we sort of have the wheels fall off the bus because we're like, I can't do this, but you can. The nice thing about bouncing balls is let's choose a direction is positive, and like I said earlier, let's take down as positive. Now, all that happens is if we chose up as positive, then your graphs just reverse, okay? So whatever I draw down, you would draw up, and whatever I draw up, you would draw down. So we're going to say, oh, no, we're not. Down is positive. Okay? Now we are going to draw a velocity time graph, a displacement time graph. So we need, got to go up, because, so there's my one axis. Should I try to draw this straight for you? Okay. There's also another reason why I don't teach maths, by the way. I can't.
Is this one of them?
Yeah, I struggle to draw straight lines. Anyway, so we have our displacement time graph. I'm not going to worry about values right now. But let's consider we're taking down as positive, okay, which means the top part of our motion is 0. So here we go, 0. Okay, 0. Remember, as the ball bounces, the velocity is getting faster and faster and faster because it's accelerating, which means my curve has to show that. So it's going to start off slowly, okay, but now it's going away from us. So it starts off slowly, and that was red, but now it's black, but that's okay. And it gets to maximum distance. But now we go, okay, so here we have this. Let's remember, and I actually just want to use this because I want a dotted line. Don't worry about the arrow. Ooh, no, I didn't want to do that. Okay. There's where it stops. There's where it stops. There's where it stops. Do you see that every time it gets to the top of its motion, it's actually below where it started, which means it has displacement. So when I keep going, I can't return to my original position because it's not there. So that means that, ooh, you know what, I know what that should, there we go. What that means is it's going to go to there, okay? It almost is like we're drawing the bouncing ball shape upside down, okay? It gets to the floor, well, the top of its motion, okay? And now it goes up again, gets to the floor, so its maximum displacement's here, it comes down, but now it's to the top, and then it gets to the top, and then it comes down again. And I would have as many little peaks as there are bounces. Okay, so this hit the floor 3 times. Ooh, my bouncy ball went for a little bit of a run. That was fun, look at that.
Yeah, it was bouncing away.
It is bouncing away.
Yeah.
It's, I hope
doing what a bouncing ball does. Okay, Tracy.
It bounces. Here we go. Okay, so it's that we're keeping at the top of its motion. Okay. Ooh, wow. This board is very, very sensitive.
Oh no.
No, I've got it. I found it.
Oh yeah. Okay.
Wow. Okay. Don't get too close.
Tracy,
apparently,
Tracy, dance quickly.
No, I'm Wi-Fi apparently. So it gets the same maximum displacement, but it changes at the top, okay? If I had chosen up as my positive direction, the graph would actually look like the bouncing ball motion, which makes it nice. But actually, I have a feeling it's the velocity time graph that's the issue. So what we need to do there is remember that it's got a positive velocity, then it's got a negative velocity, then it's got a positive velocity, negative velocity. So that means that we need to have a graph that has both positive and negative values, and that is not a straight line. Okay, and unfortunately I'm going to have to go through this quite quickly. It sounds like we might be running out of time a little bit.
We've got about 6 minutes left.
Okay, yeah, sorry. This does not want to be a straight line. Let's just pretend. There we go. There we go, straight line. Brilliant. So, starts positive velocity. Okay, and I'm going to keep the pen. Positive velocity gets to 0. Okay, positive velocity gets to 0, returns back. Okay, now, this is where it gets a little funky because it hits the ground and goes up again. There's no space here for you to go, oh, well, there's a bit of a grade. No, it's instantly in the opposite direction. So actually, we need to draw one that does this now. Okay? And then what would happen is we'd have the third one that does this, goes positive to negative. But I'm hoping you're all going, but you can't have a graph that just has empty spaces. Exactly, you can't. So what actually needs to happen is between these, you connect them, not like that. Let's try this again, with dotted lines.
So Rory Sung says,
yeah.
So basically the first bouncing ball graph is just the upside down drawing of the ball's path.
If we've taken down as the positive direction,
okay.
yes.
Okay.
It's exactly what it is. That's the nice thing, is that shape actually does look like a bouncing ball.
Okay.
Either upside down or the right way around.
Huh.
Yeah.
Fantastic.
So I'm hoping that helped.
I'm sure it did. So do we actually have time for one more question?
Quick question.
One more, okay.
We'll try.
Tracy, I hope it's really quick because I know I'm going to get into trouble if I don't ask it. So I'm going to ask it really,
I'll
really
talk
fast.
fast.
Okay, Valentine, Einstein, Ngoma. You keep giving me problems, boy, I'm telling you. But this, you see, don't worry.
Yes.
He's been helping out on the page the entire week. He's fantastic.
Oh, brilliant. Okay,
and his question is, how can a body moving at a constant speed undergo acceleration?
It can't. It's a contradiction. So if you're telling me it's constant speed, it has no acceleration. If it's accelerating, then, oh, no, I know it. Okay,
let me read it. Do you want me to read the
no,
question again?
I know what it means. Okay.
Okay.
Because he used the word speed.
You must be careful because Einstein...
No, I got it. He was using the word speed. Speed is a scalar. So we can have an object, for example, going in a circle, okay, that has constant speed, but in terms of vectors, has an acceleration because the direction is always changing. So his velocity is changing because he's going in a circle, but the actual speed is staying the same. So you can have it, but only when things go in a circle.
That's amazing.
So that one's got me.
Valentine, I hope
Excellent.
that we answered your question. I think we've got about literally a minute left. So I just want to go through, guys, please tune in tomorrow. Live shows again, starting from 4 p.m. and then at 5 and then at 6, same time, same place. Please chat to us on our Facebook wall and on Twitter. Before we go, I just want to read a few messages to Tracy because I love making teachers blush.
Okay.
Let's have a look. Lebza cannot believe that we said her name online and they're loving it so much on Twitter. Everyone says that they're going to get fantastic passes and they're going to do amazingly well. Guys, this is only the beginning. Tuning in from the beginning, I promise you're going to ace those exams. Learn more, learn extra, and thanks for joining in, and we'll see you tomorrow. Bye, guys.